of slicing in addition to the one that I just mentioned, which is called policy slicing. It turns out, and again, this is the property that we proved, that you can use the scope to create a database index for your policies. And based on that index, you can effectively select a subset of the policies that are relevant to a given request and evaluate those instead of evaluating the entire policy set. Why is this important? Well, in real life, people are protecting millions of resources, and they have tens, hundreds of thousands, and even millions of policies. No matter how fast your evaluator is, if you're evaluating all of them on every single role, things are going to be done. So you have to have some intelligent method of selecting the subset of the policies that are relevant to evaluate in order to achieve a correct authorization decision. So the scope allows us to perform that indexing and do it efficiently. Yes?
So policies are rows in a database?
They're stored in a database. So it depends. The open source version of Cedar doesn't have database associated with it. You manage the policies however you want when you store them. There is a service that you can sign up for at AWS that will do this for you. And within that service, policies are stored in a DynamoDB database.
So if someone were using Cedar on their own and they were responsible for providing their own storage for policies, could they still take advantage of this slicing thing to generate indices?
Absolutely. So the slicing algorithm is published. It's like in the paper and proven correct, and you can just re-implement it yourself. It's pretty easy. Like we have the lead code for it, right? It's about this big. The Rust code is a bit bigger, but it's pretty straightforward. Yes.
Can slicing apply optimization to twins like conditions that they be floated up basically, or is it always exploding right explicitly still?
Yeah, that's a really good question. So the base algorithm has been proven correct. It's just using the scope directly, but nothing is preventing you from actually, for example, using the SMT solver to check that the entire policy implies one of these conditions and just pushing them up. So that would be cool to do. Totally possible, we just haven't done it. Yes?
So if you have multiple scopes within your policy, does that mean it translates into multiple queries?
How the slicing algorithm actually works is it looks at the request only. So the request tells you who the principal is and who the resource is, okay? And you know who the ancestors are of the principal and the resource. So what you need to do from your database index is retrieve all policies that mention that combination of principals and resources and their ancestors. And if you get that combination, you're guaranteed to pull all the policies that would not have evaluated to false if you were to evaluate them. So it's an over-approximation. It basically pulls in things that may evaluate to true. If it can prove from the index that it's going to evaluate to false, it will not pull it in. So the index examines the scope, and then based on the scope, it pulls in the policies that are relevant to that scope, in which that scope actually evaluates to true. Yes?
So if I understood it right, Cedar uses SMT to check the policies, right?
Yes, we're going to get to that. But the evaluation, like the authorization part, there's no SMT solver. There's just like straight Rust code that evaluates the policy. Indexing, there is no SMT solver. You could be clever about it, and you could use one, but the straightforward implementation is just to look at the scope and use this deterministic algorithm to pull the policies from the index. Okay, so that's the language design. This is why Cedar looks the way it looks, and this is why its semantics is defined the way that it's defined. So we wanted to get a certain level of expressiveness, a certain level of ergonomics. The next thing we're going to talk about is this type safety and analyzability aspect, which is unique to Cedar. So it turns out that I lied a little bit. Okay, just a tiny little bit. Cedar's, when I said that, Cedar has a type checker and will reject policies and whatnot, that's all of that is true. But this type system is optional. So Cedar has a fully defined dynamic semantics. It will not do weird things if you pass it incorrect type type incorrect context, right? It's just going to error with a type error. What the optional type system does is it guarantees that if your policies passes the type checker and your request and entities conform to the schema against which you type check it, then there are not going to be any type errors ever on time. So I'll show you an example of what a schema looks like. So you've seen an example of a policy, and here is an example of a schema. So it's basically a set of type declarations that are telling us what types of entities are present in the store, how those entities may roll up to each other in that entity hierarchy using the in operator. So this is an upper bound, okay? So when I say that type user is in type team, I don't mean that every user must be in a team. I'm saying that a user may be in a team, okay? So it's giving us an over approximation of the entity hierarchy, what can appear where. So teams can roll up to teams, users can roll up to teams, but users cannot roll up to users, right? It doesn't make sense in the context of this application. So in addition to telling the type checker these hierarchical relationships, the upper bound of them, you also tell the type checker what attributes you have and what their types are, okay? So this type list has readers, which is a team, same for editors, tasks, name, and so on. Now, we support optional attributes as well. I don't have an example here, but if you wanted to declare an attribute optional, you would just put a question mark after its name. So for example, if the resource didn't have to have a name, it may have a name, you would just say name question mark to indicate that. Yeah.
So does the user of Cedar need to write the right
Schema. Yes.
Okay.
Yeah. So the developer who builds the app, they write the schema and they write the policies. In real world, the people who develop the schema and the people who write the policies may not be the same people. There may be like 50 people on one side, 60 people on the other side. Usually what happens in these big distributed systems in these apps, there's a team that defines the schema. So here's a description of my system. I'm going to provide these API endpoints. These are the types that can go in. The API points represent actions. And then the other teams who invoke them can write policies against that schema. In a simple setting, it's the same person who writes the schema and the policies. In the real world, usually it's like different sets of people who do it. Yes?
Which one of those will be the source of truth?
The source of truth is the schema. So that's your type declarations, and you want to check whether your policies are valid with respect to this set of type declarations. And valid in this world means that if I were to evaluate this policy that is valid against the schema, assuming that it is, against a request that conforms to the schema, and I'm going to explain what that means, and entities which conform to the schema, then I'm never going to get a type error at runtime. So here is an important part of the schema is this action bit. So actions are actually special kinds of entities, and you can think of them as polymorphic method signatures, right? So it says what principal types and what resource types an action is allowed, can be applied to, right? So when you're constructing your request and you choose an action, then the set of principal types that you can put in that request is limited by the principal declaration here, and the set of resource types that you can put in the request is limited by the resource declaration here. So in this case, I'm giving you a very simple example because things have to fit on the slides. And in the simple example, the action get list applies to only one principal type, user, and to only one resource type, list. In general, this can be a set of users and a set of lists. So the polymorphic signature of the action is the cross product of those types. Okay? So when we're doing type checking, we're going to have to check against that cross product. So let me tell you a little bit about how the type checker actually works. So this is where the scope comes in, right? So the first thing that the type checker does is it looks at that action constraints, and then it figures out which action declaration that thing applies to. So here it says, oh, well, this person is trying to write a policy about the get list action. Well, what must be the type of the principal and the resource for this action? Well, principal must be user, the resource must be a list. Okay, so now I have that in my type context. Then I move on, and I type check these two expressions, so resource of editors and resource of readers. So remember that at this point, I know that the type of the resource is a list. I know that a list from the schema declaration definitely has these two fields. They're not optional. So I'm allowed to access them without checking that they're present. So I access them. This is all good. And I know that the type is T. Okay? So I have now type checked the right-hand side of both of those in expressions. Next, I type check the in expression. And I conclude that this in expression is okay because principal is of type user and resource of readers and resource of editors of type T, and the upper bound on the in operator says that this is allowed. If I change the declaration of readers, for example, to be a user, what would happen? Yes?
You can't do principal in resource.readers because a user can't be in a user.
From what I've said, you're right, but that was a bad question. I should have picked another one. Let's say resource of readers is an application. In that case, your answer is correct. The weird thing about the in operator that I forgot to mention is that it's reflexive. Yes, so user would actually be allowed, but you are correct in the example that I should have given. So the type checker would reject it if the resource of readers was an application, because users don't want applications. Okay? Now, the type checker can protect against all sorts of interesting errors. You know, it can detect improper entity relationships, misspellings of actions, unrecognized attributes, and so on and so forth. The thing that's interesting about it is that it is path sensitive at the level of actions. So essentially, the way that the type checker works is that imagine that that get list action didn't apply to just user and list. Maybe it applied to both users and bots, and to both lists and albums, right? In that case, the way that the type checker works is going to take the cross product of those two sets, and then it's going to type check it in every environment in that cross product. So it's actually path sensitive with respect to the method signature. At the very top level, we do this block, and that's how we do the type checking and get the required level of sensitivity. Inside, when it's checking those optional attributes, it is flow sensitive, okay? So if you forget to check that an optional attribute is present before dereferencing it, it will complain. But if you check, it will not complain. And of course, this is approximate, so we're not actually trying to prove that you checked it. So if you write something super weird, for which you didn't necessarily sort of decide whether it's been checked or not, we would just reject it. But we're going to catch common patterns like in conditionals. You know, if you checked it in the branch in which you checked it, it holds or ends, we'll check that as well. So we approved in lean, so the type checker is modeled in lean, it's executable. The code that you might have downloaded, you can actually run the validator right now, and you're going to be running our lean code. So we have proved that this type checker is sound in the sense that policy evaluation will not exhibit any runtime type errors, or actually a bunch of other errors that we guard against if it satisfies the schema. Okay. Questions before we move on to analysis? Okay? Yes?
Can you go back a little bit? I was curious about differential testing. Like if I'm a developer ready to add a language feature, what does that look like?
That's a good question, and we're going to get to it in like 7 slides. Okay, so, well, type checking is cool, but in some sense, it's a pretty shallow analysis, right? It only tells you whether you got your types right. It doesn't tell you anything about whether you got the logic of your policies correct, right? Whether it actually satisfies whatever invariants you had in mind when you wrote those policies, right? So for that, we use S&T-based policy analysis, and that's going to answer universal questions about the behavior of a set of policies, right? Universal question means you know, can you check that for the infinite set of all possible entity store states and all possible requests, this property that I care about actually works, okay? There are many checks that you perform. If you play around with the analysis, the open source one that you downloaded, you will see a bunch of them. But the one that's easiest to understand is the classic, which is equivalence, right? And the equivalence check says it will check where two policy sets produce the same authorization decisions on the entire universe of all entity stores and all requests. And this is super useful if you're doing policy refactoring, right? You really want to make sure that your refactoring didn't mess anything up and you preserve equivalence. You were happy with the old one, it was just ugly. You refactored a little bit, you want to make sure that you didn't change the semantics, you didn't change the behavior. So here's an example of a refactoring. I have two policies here. The first policy says that the principals, all the principals are allowed to perform this create list action and the get on list action on any on this tiny table application. So any principal is allowed to create lists and to get the list, see the list that they own. The second policy is the forbid policy. It says that interns are not allowed to create lists. So you don't want them doing crazy and making a bunch of lists. So we're just gonna forbid that. Now imagine that you wanted to rewrite this policy set to not use that forbid. And you want to make it a bit shorter, a bit nicer to look at. Forbids are perhaps hard to reason about. You want to replace it with a single policy. Here is a policy that is supposed to do that. So I'm going to let you all stare at it for a little bit, and you can tell me whether these two policy sets are actually equivalent. Yes?
They are not, because the first one forbids interns from getting their own lists.
Close, they're not equivalent. And if you ask the analyzer whether they are, it will say no, and it will return a concrete counterexample. An actual synthesized request and set of entities on which one policy set allows a request and the other one doesn't. So let's see what's happening in this counterexample. It's saying that Aaron, who is an intern, is allowed to perform get on list action on tiny to do, but it is not allowed on the other side. So the SMT solver came up with a concrete counterexample, like an actual test case, and we have a tool that can generate test cases from these things, an actual test case that you can run and convince yourself that your refactoring is wrong. So we can fix this just by strengthening that one condition, and in that case, when you run the analysis, it's going to come back and say, yeah, these two things are actually equivalent. They admit the same set of requests. So how does this work? We're going to dig a little bit into the details because, well, I think it's super interesting how this works. But it works by a process which we call symbolic compilation, and that involves taking a Cedar policies and compiling it to a semantically equivalent SMT formula, and then taking whatever property you're checking equivalence and whatnot, and emitting an assertion that is the negation of the desired property. So why do I emit the negation of what I want to check? Yes?
So that you can get a counterexample?
Yes. So this is, so all of the SMT-based tools that you might be familiar with or that you will become familiar with, they use the same trick, which is basically called equivalence of unsatisfiability and validity, meaning that in order to check that a property that I care about holds, meaning that it's valid, I'm going to ask the SMT solver to search for the negation of that property. If it finds a model that's a counterexample that shows that my putative theorem is not a theorem, it's actually invalid. If the SMT solver fails to find a counterexample, and we trust the SMT solver to perform a full search, which it does, we trust it, then we have proven that the property is valid, that it actually works. So that's what we do. We translate these things to equivalent formulas, we stuff them into the negation of the property we want to check, and we admit that assertion to the SMT solver so it can solve it. So let's see how that process works. Essentially, what I'm going to walk you through is how we perform this compilation and what the challenges are. What we want to end up with at the end is a formula and a subset of the SMT logic that is decidable, meaning it's going to be in decidable theories, and the combination is going to be decidable. So in our case, the theories that we use are uninterpreted functions, bit vectors, very small subset of strings. That's why we limit that wildcard operator to something very simple. Abstract data types, ADTs, and finite sets. Okay? So what the symbolic compiler takes as input are three things. The first one is a symbolic request. I'm going to call that row. And that represents the set of all concrete requests of the right type, for your policies. The second one, which I'm going to call sigma, stands for state, it represents the symbolic store, which is a symbolic representation of the set of all possible concrete stores that are consistent with your schema. And then I take an expression and I produce a term in the SMT language. Now, when I use that term to construct the negation of my property, I'm going to show you, there are two challenges that make this really hard to Cedar. So I'm going to show you what the challenges are and how the translation works in the next few slides. But I'm going to use a simpler policy and a simpler property than equivalence, because I don't want to be translating that many things on the slides at the same time. So we're going to use this schema that I'm showing here, right? It's the time to do schema, but I've aligned the things that are not relevant, and I added an action called update task, where the allow types, principals, and users, and for the resources are list. Now, our permit policy says that the principals are allowed to perform the update task action on any resource as long as the principal is an editor on that resource. So it seems fair enough, right? The property that we're going to check is whether this policy evaluates to false on all input consistent with the time to do schema. Why would you care about that? What would it mean if I prove that this policy evaluates to false on all inputs?
It doesn't do anything.
Yeah, the policy is useless. It probably means that you made a mistake. Because why would you write a policy that's semantically equivalent to false, right? There's no point. Okay? So this is actually one of the checks that the tool that if you run it is going to perform. So it's going to perform this uselessness check. By the way, do you think this policy is always false? No. It would make for a very interesting example if it was. The SMT solver, we just not be giving a counterexample. And I want to make you give me counterexamples so I can show you some of the challenges that arise during compilation. Okay, so how does the compiler work? Well, the first thing that we're going to do is we're going to use the schema to construct the variables and to set up the data types that the SMT solver is going to work with. So we're going to use these entity types. We're going to use their declarations to introduce equivalent SMT-based declarations into my SMT script. So how many of you have seen SMT scripts before? Okay, a couple, yeah. So this is basically SMT lib scripts are a Lisp-like language in which you have these commands which are introducing data types, functions, and finally assertions of the formula, and you can instruct the SMT solver to search for a model of the format that you have constructed using this language. Okay? This is going to be less, everything is fully parenthesized, prefix notation, hopefully fairly familiar. So in this case, we're going to represent the entity T type using an ADT, where all of the members of this ADT, called T, have a field which gives you the name of the team. So remember that every entity reference consists of the type and the name. So this is exactly what we're representing in the SMT formula. Just this reference. Now for each of these types, we're also going to introduce an uninterpreted function Okay, so this is a variable in the SMT formula the solver has to solve for. An uninterpreted function that maps each entity of the given type to the set of all its ancestors. So the same trick that we were using in the concrete evaluation when we were reasoning about the ancestor sets, the transitive closure of that graph, not the graph itself, we're using it in the encoding here as well, okay? So we're representing the ancestors of a given entity using this uninterpreted function from teams these ancestor sets. Now we do the same thing for users, and we're going to do the same thing for lists, which is going to give us something more interesting to look at. So lists have attributes as well, and we represent attributes as uninterpreted functions from entities to records of the right shape, where the shape of the record is defined by the schema. Yes?
What does uninterpreted mean here?
Uninterpreted function means that it is basically a function whose body is unknown. It's a variable. The SMT solver is going to come up with a body of the function, if it can, such that it eventually satisfies the assertion that I'm going to make. So, uninterpreted function, SMT speak for a variable which is a function. The next thing that I'm going to do, so this basically, by the way, when you stare at this and you remember that these functions are variable, this declaration in the SMT language symbolically represents every single concrete store that is consistent with this schema, right? I've just encoded the types, and I place no constraints at all on the contents of the attributes and the ancestors. The solver is free to pick them. So it represents everything that can happen. So the next thing that we're going to do is we're going to generate the concrete, the symbolic request, and we're going to do that by looking at this action declaration and looking at the type that is allowed, in this case the user, that's going to be the type of our principal variable, and the list is going to be the type of our resource variable. Now in SMT lib, declare constant declares a variable. Okay? They're called symbolic constants, but they're actually variables. The SMT solver is going to search for a binding of these variables along with a binding for these functions that try to satisfy a formula that we give it. I haven't given it any formula yet. I'm about to do it. Okay? So here's the formula that I'm going to give it, which is the encoding of the semantics of this policy. And I'm looking for a negation of what I want. So what I want is where this policy is false, and negation is where this policy is true. So I basically taken this policy and translated its body into this equivalent SMT formula. So what is it saying? Well, it's saying that this policy is going to evaluate to true when we retrieve the attributes of the resource, we retrieve the editor field of those attributes. We are going to obtain, as you can see from the type declarations, something of type a team, and this team is going to be a member. So set member is a built-in operator in the theory of sets. So it's going to be a member of the ancestors of the principal. And note that the compiler is smart, right? It's done a lot of optimizations, and it's not emitting spurious things that it actually can prove are true through the compilation process. So it's only going to emit a residual for which it rewrites rules are not strong enough by itself to prove that they're true. So the things that it cannot prove by itself, it's going to emit to the SMT formula and ask the SMT solver to find a solution. In this case, the solution is going to take the form of a model, which is a binding of all the variables to the values that make the assertion true. Okay? So, is there a model? Yeah. Here's one. Now, CVC5 is the correct solver. It outputted the correct model. This indeed satisfies my assertion. But there are two problems with it. Something weird is going on here, right? So the first weirdness is that my definition of the ancestor relation doesn't satisfy acyclicity. If I have a DAG and I take the transitive closure of that DAG, the relation that comes out is going to be acyclic and transitive. But here, it's not acyclic. What SMT solver is saying is that every single team has the SMT solver violated acyclicity. Well, why wouldn't it, right? Like, I didn't tell it not to. I didn't give it any reason not to. So it picked that as a model. So that's not problem number one. Problem number two is it violates transitivity, okay? So here it says that every single intern, every single user is a member of the intern team. But if this was properly transitive, if you're a member of the intern team, you should also be a member of the build team. So this is violating both acyclicity and transitivity. It is actually not a valid counterexample from Cedar. This would be considered a false positive, right? This does not translate into any hierarchy that I can display to you. So what are we going to do? Well, we have to somehow tell the solver to make these things transitive and acyclic. The obvious way to do that is to use a quantifier. But if you use a quantifier, what happens? Yes? We still need an SMT solver, but you break out of the decidable fragment. You're undecidable. And we want to remain decidable. So what do? We use this neat trick by which we observe that because the Cedar policy is free of loops, that means that the number of entities that it can reach through any execution is finite. We can statically over-approximate this finite set. And we can ground the acyclicity and transitivity constraints on this finite set and only omit those. We call this finite set the footprint, and it is effectively, to a first approximation, it's actually a little bit more clever than that, but to a first approximation, it is the subset of all, it is all the sub-expressions in the policy that are of type entity. Okay? So in this case, there are two relevant sub-expressions. And what we're going to do is we're going to omit all the acyclicity and transitivity constraints that are relevant to those two sub-expressions. So the first one is acyclicity, okay? So teams can roll up to other teams, and we have to prevent the cycles there. So we're going to say that it's not the case that the editor set is a member of its own ancestor set. Okay, so the editor team is not a member of its own ancestor set. And then we're going to omit the transitivity constraint that relates the principal to the resource of editors. Okay? So this is a finite number of constraints in a decidable fragment. We're remaining decidable, we're still decidable, and we're now going to rule out some bad cases. When we rerun the SMT solver, things are still going to be satisfiable, and they're looking better now, okay? But we're still not out of the woods because we still have a cycle. I have omitted the acyclicity constraints on the footprint, okay? So anything that's reachable from the policy variables by chasing the pointers that get you to an entity, right? But I have not ruled out cycles and everything else, right? So how